Thanks to Dave McCallum and Khalid Musallam for inviting me to give this presentation. As was mentioned, this session is on use cases, so I'm going to try and motivate how SimCenter tools could be useful in allowing the community to access simulated ground motions in their work. So, how do I get forward here? Okay. So what I view as SimCenter's role, just before I get started into what SimCenter is, this would be the major point I want to get across in this talk today, is I view our role as how we can provide tools to allow researchers and practitioners, such as yourselves, to feasibly make use of these simulated ground motions in their computational workflows. So that's what I see as our benefit related to this two-day symposium. And what I mean by feasible is reasonably easy to use, and by reasonably easy access to simulated ground motions, simulation models, and HPC resources. So hopefully I'm going to try and make that connection between, I think, how our tools could help users access these ground motions in that way. That's really the point. So I'll start by introducing SimCenter and then show some of the applications we've developed which might move towards this direction. So SimCenter is one of many NEARI facilities. We're funded by the NSF, and we are one of a few non-experimental facilities. Most of these facilities you're familiar with. They do large-scale experimental research. Us at SimCenter and then at UT Austin are the computational facilities, and that's design safe. And so our tools make use of design safe supercomputers to allow users to access those and do their running. So we're here at SimCenter. Our mission is to basically simulate the impact of natural hazards on structures, lifelines, and communities. We create open source software to do this, an extensible application framework of software, and what we say is next generation of regional disaster simulation tools. And those regional disaster simulation tools really connect in with the mission of this workshop again. And we also provide education and training and documentation for these tools. It's a very large team. I'm just one member representing the work of many very excellent people who have devoted a lot of time to this. I'll acknowledge Professor Dearlon at Stanford, who's the co-director with myself, Frank McKenna, who's sitting here in the front, who's the brains behind all the software implementation and development on our team. And also in the audience is Jinyan Zhao, who Jinyan is a postdoc who's responsible for the regional earthquake part of our workflow, so someone you might talk to if you're interested in getting involved with our team. But we have a large developer team developing software, and we have a huge number of faculty domain experts who are allowing us to do hopefully useful work in all these vast areas. So what are we doing? We're doing everything in the workflow. I would say we're allowing researchers to more easily do more complex computational workflows. So this is an example. We develop tools, software tools to develop asset inventories, whether that's lifelines, buildings, road networks, pipelines. Where we connect into this community is, can we see this good, is the event intensity. So in this case, it would be earthquakes. We're also dealing with other hazards, but this is where the ground motion simulations would plug in. Then we're allowing users access to simulation tools, structural simulation, pipeline simulation, transportation simulation, to understand behavior of your system or your asset. And then we're moving into damage and loss and recovery. So we provide applications through this whole workflow. And the way we view this is a kind of a group of puzzle pieces. So if you're doing research in describing a hazard, or in this case, creating simulated ground motions, you do this red puzzle piece. And if we can plug this into our framework, it can allow other users who are doing all the different parts of this puzzle to connect into the results of your research and use it in theirs, basically. So we are funded not to do fundamental research, but to be a tool or a support for people doing research and allow them to kind of access these tools. Overlying this all is uncertainty quantification and supporting databases, which is a huge aspect of our work as well. So I'm going to skip through this. I'm going to talk through a few of the software applications that are most relevant to this audience. So these are all of our software applications on one rather busy slide, but we're doing software applications in earthquakes, wind loading, tsunami. So we call these are our three different kind of hazard-specific areas. So I'll just focus on the earthquake engineering one today. Then we have an application that uses all of these to do performance-based engineering computation. So how do we get from response to a level of damage or the implication of that damage? And then this last one, which I think is particularly interesting, again for this audience, is R2D, which is a regional resilience simulation tool to allow us to do extend our simulations to larger areas. So this slide, I just want to say one thing. Here's our applications in the middle. What we allow users to do is to download these tools they're free for anybody to use. They're open source to their own computer to run small simulation jobs, or they're already integrated in TAC, so you can run simulations jobs for free on the HPC resources there. Okay, so let's go through these three applications I mentioned. I'll start with the earthquake engineering application. We're trying to provide, again, users ease of access to hazard definitions. So we have many different options for users. There's a user interface with drop-down menus, so you can pull in stochastic motions. You can access the peer NGA database. There's a variety of others, which I'll talk more about in a minute. We also provide access to OpenSeas or other simulation tools, but there's also users can connect in their own simulation software, like that puzzle piece diagram. If you have a different simulation tool you're using, you can still access the workflow on the hazard, then use your simulation tool, and then do the performance-based engineering after that. So a couple more words on this PBE tool. So these are the logos for our tool on the top left, the EUQ, and then the performance-based engineering tool. This is based on something we call Pelican, which basically takes the results of your simulation and translates them into damage or the implications of that. So we use HAZIS, that's integrated fully in our tool. We use FEMA P58. These are guidelines or fragility curves, libraries of fragility curves that allow you to do that extension of your work. I should say these fragility functions are for buildings and they're for earthquakes, but they're across a huge variety of things. They're also for pipelines, as I said, for roadways, also for hurricane damage and other sources of natural hazards as well. So if we look a little bit more detail into the R2D application, which is the regional one, again, this covers multiple hazards. So you're defining your hazard here, or your ground motion simulation here. We also support hurricanes and tsunamis, and as I said, buildings and lifelines. A big part of this is defining the inventory. So these are the three kind of phases of this on the left. Whoops. This first one in asset definition. So we allow users to, in detail, define their assets at the parcel level. This comes from existing databases, building inventory databases, which we have plugged into our tools. It also comes from an application we call Brails, which is an AI tool to kind of do automatic detection or recognition from images of building typologies to allow people to create their own regional inventories if they want to do regional simulations. So we have test beds where we've done this, but again, we're not providing that. We're providing a tool to allow a user to create their own inventory for their own region if they want to do that type of simulation. Then I talked already about the hazards. So we have many different types of hazard definition. I think in the interest of time, I won't go through all of these, but many of the existing ground motion prediction equations and other earthquake hazard tools are already in there. And then last, when we get to response damage and loss, I just want to highlight, so these are visualized in an interface, so it allows people who are doing these types of simulations to relatively easily use this interface to present their data, present their response, and to show the implications of that at a regional scale. Okay, so a couple of examples of how that's kind of an overview of the tools, a couple of examples of how that could fit into this community. So we've done several regional test beds, San Francisco Bay Area, which I'll focus a bit more on in a minute, an Anchorage, Alaska hindcast, and then these two are hurricane related. But we created these test beds as example use cases. Also, they're test beds that the data is freely available for anybody to go get that data, and then to, if they want to do other things with that data, they can access and use that as well. So the San Francisco Bay Area is directly fits into the mission here. This was taking the Hayward fault simulation scenario, which many of you are very familiar with, and that was the hazard model there. We have a high resolution building inventory, so we have 1.84 million buildings. So again, at the parcel level, we're using building databases to create a small simulation model of every building in that whole region. Then we're doing, it's an OpenSea's idealized MDOF model. We're doing a simulation of that building based on this distributed simulated ground motion. We're using HAZIS to then get to damage and loss. Some uncertainty quantifications, not too many realizations because the number of buildings that are involved in this simulation, but this was done at Stampede. This is a few years ago, and you could see the runtime there on 10,000 cores. So again, what we're pushing is that with this tool, you could do what's on the left rather than what's on the right. So you could simulate individual response at a parcel level. So you can make use of the detail that comes out of these ground motion simulations at a very local level rather than a more aggregated HAZIS-based thing which takes kind of regional averages of damage. I think I'll skip through a little bit. This was meant to show the existing hazard models that we have integrated, so what types of ground motions you can pull in already and how you can use them, but many of you will be familiar with this. If you want to use them, go to the website, download the tools, and you can see in the documentation all the different hazard models are in there already. But I think these simulated earthquake scenarios, these large databases of simulated earthquake scenarios, our view is that we just plug those in and a user can just select that in a drop-down menu and access those and run their simulations using that type of data. Now how we do that is obviously easier said than done. So I'll just skip through some of these on what we're doing now. And I go to a couple of applications. So I've already reiterated this a few times, but we're dealing with buildings as well as other things. So this is an example application for buildings where we're looking at downtown San Francisco. And this is a visualization of the result of that case. We have transportation infrastructure. So this is something we're really pushing now. So we have the HAZIS fragility functions input for those as well. So if you're interested in transportation infrastructure, you have your ground motion simulation. You can model the damage to your existing road network using fragility functions. And now at the moment, we're also, as Kenichi just showed, we're integrating these agent-based models to do traffic simulation, so you can show the implications of that damage with regional scale simulation. And the same thing with pipelines, and I think Kenichi already went through this, but you can imagine the workflow that he just demonstrated. Integrating this into workflow where you also do buildings, you also do transportation, and you do pipelines together allows us, as we're pushing forward, to look at interdependencies between these. So one example of that was Alameda Island, which Kenichi also mentioned. So just to give a visualization of what this might look like, we're using a wide variety of tools to get the inventory. Braille's there is the AI one, but these are also building databases. Then we have here the total inventory demonstrated. We have the transportation and water inventory, and right now we're using the ground motion map to a grid, which is shown here. We do a nearest neighbor type thing where we allocate every single building to the nearest neighbor and use the ground motion there to simulate the response of that asset, whether it's the roadway, the building, or the pipeline, and then we can simulate the effects of that scenario. Okay, the last thing we're pushing at the moment right now, these tools aren't available yet, but we're hoping to get them available in the next few months, is more on the recovery side. So once we've got that damage mapped for a region, how do we simulate the recovery process? We do have some things in. These are very, what I say, simple recovery models, just a recovery curve, just like a fragility function. You have a recovery curve, and those exist in various documents here. These are the ones that we're integrating into our tools. That just says if you have this level of damage, this is how long it takes to recover. It's simple, straightforward. It doesn't really deal with the complexity. But what we're really pushing towards is the interdependencies. So what you have with R2D now is you have a simulation, you have damage and loss, you have a simple recovery model, but then what you want to do is also incorporate uncertainty better into that, and you also want to look at interdependencies and resilience after that and how long the whole region takes to recover. So we all kind of have an idea of what resiliency or recovery looks like. Resilient, this is kind of resilient, this is not so resilient, you know. How long does that recovery take? We kind of understand the damage pretty well. I don't think we understand at all this recovery very well. So we're trying to provide tools again for other people to investigate this area a bit more. And what we've decided now to do is to integrate something called PIRI codes. PIRI codes was developed by these two citations down here, and this slide was provided by Nikola Blagojevich at ETH Zurich and Bojan Stojadinovic, who was a former professor here. They developed this PIRI codes, which is a recovery module. So what we're doing so far is we have our hazard, we have our vulnerability, or we have our damage. We've done this part on the left already, but how we do this recovery and how we quantify this resilience. When you have an event, how long does it take to recover? And the way they've done this in PIRI code, so we're integrating these two at the moment. The way they've done this is a supply and demand model. So it looks like all your areas of your city, you have some sort of supply of resource, whatever that resource is. You have some sort of demand, and you have that all over, and you then try to do a resource distribution model where you say, for my water network, I have this supply of demand, for my power, for my housing, etc. And it's basically a time-stepping algorithm that allows all of these different things to talk to each other based on a supply-demand model to see how long things would actually take to recover. Well, now there's tons of assumptions within that model. I'm not saying that's a correct model or it's a good one, but I think it's a push in the right direction to try and be able to simulate these type of things. Again, this slide was provided to me. This is a residential building case study in San Francisco, and it's just a visualization which says, these are all the steps it actually takes to recover. Some people are waiting. They're waiting for inspection, financing, cleanup, architecture design, permitting, demolition, etc. And stepping through all of those steps takes time, so that's just for the housing part of it. So it's trying to quantify the supply and demand for that aspect, and then you would do something similar for your pipelines and your roadways, etc., and try and get all these things to talk to each other. So for pipelines, we're integrating HydroSim, which is the hydraulic simulation model of Kenichi's group. Also REWET, which was developed at the University of Delaware. For the transportation model, we're using spatial Q and I think residual demand models as well. So again, our job as SimCenter is to take these open source simulation tools, which other people have developed, to plug them in and allow other people to use them. So if we have a water model, a transportation model, then we have a recovery module to integrate in there. Other people can take these, and again, they can fill in their part of that puzzle and also have access to these other resources. So I'm nearly out of time, but I added a couple more slides at the end to talk about, I think, two different problems which are fundamentally different in using the ground motion simulations that might come out of the work done here, and how we would plug those into our workflows. So one is taking those and doing simple 1D site response to our buildings, if you're thinking about regional simulation, or the domain reduction method, which was discussed yesterday, to do a much more detailed evaluation of a single asset. So we're integrating both of these options, and then users can decide how they want to use them. So for the 1D site response, we're saying, well, if you give us rock motions everywhere, we can provide a 1D site response locally, and we can put that in our regional simulation. This slide was provided by Pedro Arduino, who was here yesterday, who's kind of leading this work for us at SimCenter. Or we can do that using the domain reduction method, so we're integrating that in the next few months, hopefully, or maybe by the end of the year at least, so people can use these ground motions with the DRM and then plug that into the workflow as well. I think we really need to look at what the goal of what we're doing is. So for the regional impact studies, the broader goal is basically decision making, right? It's public policy, it's infrastructure operation and preparedness, retrofit mandates, urban planning. Then the simulation goal is regional risk, evacuation, recovery, resilience. The ground motions that we require for that are much different than what we require for the other problem, which is a very detailed simulation of single building. I know this is obvious, but when we were talking about realizations yesterday, like we really need to define that end use case and how a user is going to use it at the end. And then we can work backwards, I think, to define how many realizations and which models we use. In this case, I think maybe our 1D soil model is good enough to make some of these decisions. But the last presentation yesterday nicely showed that if we're looking at very detailed simulation of fault response or a single building, these DRM methods could be very useful to people as well. So I think I'm out of time. Here's just, I'll just highlight the website for the SimCenter. Download the tools, play with them. Our main objective is to serve the community. So if you have tools that you think, oh, I have a ground motion model that should be in there that other people could access, contact us, let us know. We can figure out how we can get it in there so it can be used by others. On the other hand, if you have some functionality that you think we're totally missing that we should be putting in there, please contact us as well. We're more than happy to do that. We also have working groups. There's actually one this afternoon, a working group on regional earthquake simulation. Anybody's welcome to join those working groups to give their input on what we should be integrating into our tools. So if you're interested in joining such a working group, then also please send me an email. Thanks.